Good morning, everyone. I have excellent news. Our final homework assignment is posted on Inkfish. For the final homework assignment of the semester, after this, all we have to worry about is the final project. What you're going to be working on is another maze-solving assignment, except this time, instead of having the laser rangefinder sensor, which is a super useful sensor for mapping and obstacle avoidance and stuff, what you get is a camera. And cameras are fun. They provide you a lot of information. You get a ton more data from a camera than you would from a laser rangefinder, and the data is super useless. It requires a ton of processing to figure out anything. And with one camera, it requires like some really difficult processing, because with just a single camera, the information that you have tends to not be at all straightforward to interpret. There's a bunch of different ways to understand what's going on, and figuring out things like distance or size of objects in the camera frame is really hard. Like, the camera by itself sometimes just straight up doesn't have enough information to answer that question for you. You can get into trickery, like seeing how things change across subsequent camera frames, based on your known motion of the robot between the two things, which can give you sort of two perspectives on an object, which may be enough information to determine size and distance. But yeah, that's a lot of work. So luckily, there's some tricks that you can use on this particular assignment to make the camera work a little bit better for you, and you're going to have to use those tricks to reasonably accomplish it. So the assignment is to go ahead and grab the starter code. It's in the hw08 directory up on the starter code Git repository. Then you want to go ahead and test the starter code. The starter code is not going to pop up a mapping window this time. It's going to pop up a camera image display window. What your task is in this assignment is to port over your mapping and pathfinding logic from homework 7, integrate it with the new camera sensor, and then use the camera sensor as your input to the mapping rather than a laser sensor. You no longer have a laser sensor with this starter code. You do get a sonar sensor, which points straight forward and might be useful, in fact is useful, and you should use it for sort of immediate speed decisions and like simple obstacle avoidance to help you avoid driving directly into a wall. And that's available because camera processing can be a little bit slow, although if you're careful with your camera processing, you probably can do obstacle avoidance with just the camera. In any case, you should be using the camera as your sensor for mapping, and then plug in the A-star pathfinding or whatever from the previous assignments to be able to get a video where you can solve a maze using this camera data and mapping. There are 2 bonus point opportunities. You can still get bonus points for bug fixes of the starter code, and you can get bonus points for using this whole thing to fully map your maze, not just solve the maze. So that's the basic story here. Let me pop up the starter code real quick. So if I say make, yeah, it looks like we didn't actually have this built, but I'll pop up the starter code, build it. Oh, you can't even see what's going on. Let me move my image. Throw myself up in this corner. So we're building. And then once this builds, which of course you want to wait on, we can go ahead and run our demo, which actually ends up being the homework 5 starter maze, I think. Yeah, it's this just square maze. And you get a robot. You can see the robot has this like red thing on top, which is a camera. can see these 4 white lines show sort of the direction the camera is pointing and give us some indication. We sort of stare at it, we can kind of guess what the picture will be from the camera. It's a square camera for some reason. It's okay. And this blue cone is the sonar sensor. So that's what we have for that. But let me go ahead and start up our brain program so that you can see what we get there. So brain. So when we pop that up, we're going to get this camera window, and let me go ahead and there we go. I'm in the wrong corner again. Let's put me down here. So we have our robot. It's looking at a wall, and we can see that the robot actually can see, looks like we have more field of view than is indicated here with this camera picture, or with these white lines. We can see some sky, we can see some ground, and we can see the wall. If we actually move this robot, I'm actually just going to rotate it. If we rotate the robot, we can see we get other perspectives on the maze. Oh, I messed with the robot too much and it flipped over. And now our robot is on top of the wall. And now our robot has launched itself into space. But in any case, you can see that we have a sort of 10 frames per second real-time camera coming off that robot, which has now been lost into the depths of space. But this camera image is the sensor data that you're going to have to work with. Let me go ahead and restart the Gazebo sim real quick. Reset model poses. There we go. And so the method that I suggest for using this camera data is actually a really simple strategy. If you start in the bottom center of the camera frame, you can then draw lines out and sort of simulate a laser rangefinder. So you'll draw a line straight forward, and what you're looking for is at what pixel in the image do you transition from floor to wall, or to anything that isn't floor. And because we have the known fact the camera is mounted at a specific angle, and the ground is perfectly flat, is a perfectly flat plane, you can do a little bit of geometry, and based on what row of the image we have this floor-wall transition, you can determine how far away the wall is, at least as long as you aren't so close that you can't see anything. And it looks like with our camera field of view, you have to be sort of super close before you don't have any floor. So I guess if you don't have any floor, you can say you're too close and do whatever, but you can do one sort of ray here, and you can do another couple rays, like starting from other locations and drawing forward, and do some additional geometry and arithmetic to figure out what that tells you about where there are walls. And this color is pretty distinctive compared to the wall color or the sky color, so you could probably do some sort of color-based thresholding or gray level-based thresholding to figure out that floor-wall transition. That's not going to use sort of the full capability of computer vision that we're going to have with the libraries that we're using, but it's a simple strategy that should let you get this particular thing solved and force you to deal with a little bit of image data and the fact that you have a camera, which is sort of my goal for this assignment. The other thing that's going on in this assignment is that the error model for this robot is way simplified. There's still a little bit of position error, but it's just completely random noise. It doesn't drift at all. And there's a little bit of error in motion commands, but mostly you have reasonably accurate position and motion that you have to work with here. All right, so that's what I wanted to cover about the assignment starter code and stuff. The next thing that I'm going to want to show you is the OpenCV library, but I'll come back with that in a second.